I'm bringing an extra vid for you, which I'm revising the model of the fins, not the drag model, the normal force model. Okay, I'm not going to talk about the aerodynamic center, which is it's alright, the model. The one that was not so precise was the CN alpha of the fins. If you recall, I used a model of Fleeman, but it's a quite simplified model. I'm talking about right now the subsonic model. Well, not the subsonic, but for Mach below Mach linear, remember? So it was equal to 2 times the specific span squared. It's a very nice simplification, a lot of stuff gets away, and it's just so easy to operate with this, and this permitted us to do a very nice analytical model. So it's still nice to do, to do all the study of the natural frequency, but it is kind of, quite inaccurate in some cases. So if you check page 66, of Fleeman, he says that this equation is not quite accurate for high aspect ratios. It's going to overpredict the effective high aspect ratio, and the same for high sweep angles. Okay. So what I did, I went to. By the way, remember I'm only doing this is for the case of 4 fins. So I didn't explicitly explain how to calculate the CN alpha for a different number of fins, which is interesting. Typical, as I told you, the typical rockets have 4 fins, but as you saw, that paper suggests using maybe 6 fins. That's something I would think of doing. So I'll just extend this to. It's pretty simple. It's just this is the number of fins. So this is extended to any number of fins. No, wait. Alright, sorry, no. Of course, this is over 4. Okay, so this is what Fleeman says, but it's a quite simplified model. So I was thinking of getting away with it, but no, not really, because this is very important. So for the analytical study of the natural frequency, after all, the goal was for you to get an idea of which the kind of the shape of the function you're going to have for the natural frequency, kind of the order of magnitude of the damping ratio. It wasn't so important the exact value. As you saw, we could still get really strong conclusions from this simplified model, which is super nice. It only depends on the specific span. So you could think, all right, it only depends on the specific span. Well, I'm going to do some fins like this, right? Because that's going to lift exactly the same as this. So this is what this function is telling you. Obviously, that's not true. So although there are some missiles that have like really strange fins that are like this, but still, you get it doesn't lift the same. Obviously, this as this. So you got to put some corrections. So the corrections I'm presenting to you in this video are, I've taken them from OpenRocket's technical documentation. I've mentioned you this document a while ago, and yeah, it's a great document. So the thing is, I don't like don't kind of like how they present all the equations. So I've massaged them a bit and presented to you. I'll present them to you in a different form. Okay, so this form will take into account new factors, taper ratio. So not ration. In this equation, it only depends on the specific span. Well, taper ratio also has an influence. So remember, it's the ratio between the chord at the tip and the chord at the root. It's also going to have corrections for fin body interactions. So the interactions between the fin and the body actually gives a plus on an extra nudge on the CN alpha. That's nice. And it also takes into account the aspect ratio. So if it wouldn't take into account the aspect ratio, yeah, you could fly fins like this, and it doesn't make much sense. It would, yeah, lift what I was saying a moment ago. Yeah, taper ratio, aspect ratio. Yeah, that's about it. So, OpenRocket presents you the equations in a different fashion. I've derived the following equations just with geometry, non-dimensionalizing, and massaging it a bit, and we finally arrive to here. I'm gonna pause the video. All right, here we go. By the way, I forgot about the sweep. Sweep actually, also influences sweep angle. A sweep of the leading edge. Okay, I just called it without the leading edge subscript here. Yeah, I think I'm gonna pause the video when I have to write like long equations, because when I'm talking and writing, my writing skills diminish outstandingly. So I'll do that from now on. All right, now you can see why I didn't want to put all this and do, and do the analytical analysis, the stability analytical analysis, because this is terrible to carry over. By the way, this beta is a correction term for compressibility effects. So it's 1 minus max squared. All right. So yeah, and now you're gonna say, all right, so what about it? What does this mean? How is this gonna influence? So look how I've presented to you this equation. I presented to you in a way that it's like a factor that changes to specific span squared. So I'll call this term the correction term, right? And we'll have to give it another variable. I don't know what I'm gonna call this. My physics professor said that when he studied, he ran out of variables and he started to use the what was it called, like the Jewish alphabet or Hebrew, or I don't know how to. Well, I'll just call this pi, capital Pi. I still have a few variables left, so we don't have to move into strange symbols yet. So what I did for you is I plotted this out in Mathematica. It's a nice program. Maybe you're more familiar with Wolfram Alpha. Is it like this? Wolfram Alpha uses Mathematica. To when you're asking it to to solve something or to plot something, well, it uses Mathematica inside, I believe. But you can also download Mathematica and use a program like independently of the website. Well, I plotted this out in Mathematica. So this function has 3 variables. 1, taper ratio. I'm not gonna talk about the beta. I'll just call Mach1. Sorry, Mach0 for this plot. Obviously, if we go on the high subsonics, this beta is gonna have an effect on this term. But for now, I'm just gonna call beta 1. So 1 term, 1 variable, 2 variables, aspect ratio, and sweep angle. So what I did for you is I plotted this correction term pi, capital Pi. So let's see. I'll fit this in. Yeah, Mathematica is nice for this. You'll see now. Okay, so let's make this big. Cool. Let's see. I called A aspect ratio, T taper ratio, and S the sweep angle in degrees. So I'm plotting out the correction term. All right. So let's see. That's right. And I'm plotting it from 0. Yeah, I should plot maybe aspect ratio from. Let's put from 1. Yeah, it makes more sense. Doesn't make sense to talk about aspect ratio of 0. So aspect ratio on this axis, on the x-axis, and on this axis, I plotted out the taper ratio. So from 0 taper would be delta wings, and 1 taper would be rectangular fins. All right. And the higher the aspect ratio, well, the higher the slimmer the fins are going to look like. Okay. So this is the sweep angle. So as you can see, this is like a contour plot. You have to. Let's see. Yeah, that's right. So please note that I've also added the interaction between the body and the fins. So I know that Fleeman says that it kind of over predicts normally this function over predicts, and the taper ratio, the aspect ratio, the sweep angle is gonna lower the CN alpha. That's true, but the fin body interaction is gonna increase the CN alpha. So the overall effect could be an increase or a decrease. And also for very small aspect ratios like 1, this kind of underpredicts. So that's why we have correction factors that can be from. All right. Sorry. Someday I'm gonna remember to quit Slack, but someday. Capital Pi can be smaller or larger than 1. Can be, oh, Jeez. I'm trying to buy some metal in China. Sorry. Sorry. Sorry for that. Alright, so pi, capital pi can be below and above 1. So it doesn't have to be below, okay? Okay, so this is for sweep angle 0, so this is... You're never going to have this because... Yeah, not a good idea. So let's put... But still you can see that the these contour lines are different correction factors. So as we see here, for small aspect ratios and higher taper, so it the correction factor is going to be really high. Okay, so for like long wings, rectangular wings, well, you're gonna have like a boost, but still, let's put something more realistic, like 40 degrees. Let's see what happens here. So 40 degrees of sweep. What happens here? Well, one correction factor is around more or less aspect ratio of 3, which is already, it's not bad, it's pretty high. And if we have aspect ratio below 3, well, we get a boost. Okay. So remember Stratus 3, I think it has like an aspect ratio of, it's really low, maybe 1.5 or so, yeah. But again, this is the correction factor over the specific span squared. So yeah, just remember that. And the taper ratio kind of only has a big effect at lower tapers. So and what it does is that for the... Okay, so think that we have the same specific span, we have the same sweep and the same aspect ratio. So yeah, it kind of if we decrease the taper ratio, it's gonna slightly decrease. We're gonna get a slightly lower lift. All right. So yeah, but for the rest, it doesn't influence too much on the shape, as you can see. So for taper ratios above 0.2, it's kind of independent. Okay. So basically, the higher aspect ratios, the less it's gonna lift. So if we... Oh no. Alright. Hopefully that's the last notification. So, okay. So, yeah, for higher aspect ratios, we're going to have a lower lift. So that's the reason why, if you were thinking that, you could get away with, some strange looking fins. Well, no, you're going to have a correction term that's going to be 0 point something really low. If you want, we could check. Yeah. Let's plot it, I don't know, into aspect ratio of something crazy, like 10. Well, not that bad. Oh, interesting. Yeah, Mathematica is nice to play around. 0.3. It's a very nice tool to have if you want to, because if not, what could you conclude out of here? I mean, there's just a bunch of terms dividing, square, tangent, whatever. Yeah, it would be hard to draw some conclusions out of there. So, okay, so let's try to put it into a couple of conclusions. So, high aspect ratio is over predicted by Fleeman's equation. Fleeman's equation is Cn alpha is equal 2 times specific span squared. He never presents it like this, but if you massage the equations a bit, you can arrive here with his equations. Much nicer ways to present it in this way. What happens at a at a low aspect ratio? So maybe on the high aspect ratio, I'm talking about maybe above 3, and lower aspect ratios like lower than 1, or 2, it underpredicts. Okay, so this is well suited for maybe aspect ratios of 2, 3. And then what about taper? Taper kind of doesn't influence too much. At least when sweep is high. The sweep angle of the leading edge is high. So when it's low, it kind of does a bit more. So you can see here at 0 sweep, we do have kind of it does influence. So we have a lower lift for the same aspect ratio and the same sweep. So at higher sweep angles, you can see that it doesn't influence that much. Okay, so it's kind of, it doesn't care about taper until a certain point that it does influence. So yeah, that's a nice conclusion as well. So it doesn't influence too much, but at lower taper we have lower lift. Okay. And finally, sweep. So this aspect ratio, talk about taper. And what about sweep? Well, sweep angle of the leading edge. We'll check it now. Let's take a look at for example, this point. Aspect ratio of 3, taper of 0.2. Okay, so at sweep equals 0, it's practically 1.06. Cool. If we increase it a bit, slightly increases, but it doesn't look like it has much influence, right? No. Yeah, really, at really high sweep angles, we do have an influence. You can see here that now, the correction factor is low. But up to a certain point, it doesn't. You don't have much of a penalty of adding sweep, as you can see. At least in this combination, I'd have to look into it. I never looked into it deeper. But it looks like, at least at this point, it doesn't influence much up to from 45. 45 is kind of standard. Let me look into this a bit more. All right, I'm back. So, okay, I'm gonna let this slider go automatically. This is a sweep angle, so we're starting at 0, and then we're gonna increase it. Don't look at the colors, because these are gonna start changing as contour lines are gonna change. So remember that bluer colors are lower. Well, correction factor below 1. Sorry. So lower lift. So as you can see, up to now, the contour plots, the contour lines kind of straightened up, but didn't really move. So we still have like contour line 1 here. In the beginning, it was, yeah, it was still here. So it's more or less in the same spot. Take a look at this contour. But now, yeah, when you get like around 40 or so, the blue starts invading. Well, at least the let's say the negative corrective factors are getting, kind of invading the plot. So here, at really high sweeps, we have really negative corrective factors everywhere. But this is 63. So up to like 40 or so, you don't really have a much penalty due to the sweep angle. So take a look at the contour lines. 1, 1.1, 1.2, 1.3. Well, yeah, 1 practically. What about 25 degrees? 0.9, 1, 1.1, 1. Yeah, practically the same. What about 40 degrees? 0.9, 1, practically the same. But when we move to 50 degrees, 0.8, 0.9, 1, yeah. So up to like 45 degrees, like up to more or less 45 degrees, there's no sweep penalty. Let's call it. In terms of the normal force, also think that the sweep brings back the aerodynamic center of the fin. So maybe you could have a lower normal force, but the moment maybe it's compensated. So we didn't look that much, but yeah, we're going to talk about the normal force. But up to like 45 degrees, we have no sweep penalty. 45 degrees, remember, it's kind of a typical angle for sweep angle in the leading edge. All right, so yeah, I think it's quite interesting what we saw in we've seen in this video, and yeah, Mathematica helps us to understand, the influence of each of these variables. We haven't introduced into the simplified version of the fins we've used up to now. So yeah, remember we've introduced 3 more factors: the aspect ratio, the sweep angle, and the taper ratio. So the one that has most influence on the correction factor is definitely the aspect ratio. The aspect ratio, it can change a lot if we have large aspect ratio or long or a short one. The other 2 factors will kind of, sweep from at large angles. Yeah, it's gonna make it lift lower, and the taper ratio, not too much, but it also does. And we've also introduced the corrections for the fin body interaction. One last thing I want to put in this video is the correction if we use more than 4 fins. So let's see, this is the Open Rocket technical documentation. So we multiply by a correction factor if we have more than 4 fins. So yeah, remember that it's interesting to add more than 4 fins because the induced roll is going to be way lower for 6 or for 8 fins. So, but it isn't proportional to lift. We have to add a small correction factor on top of this. So I'm gonna end the video adding just a little. This is times number of fins over 4. and then a correction factor, the correction factor that OpenRocket talks about. All right, correction factor. So this is always below 1. Not too much, but yeah. So we'll leave it here.